Hello, my name is Gregor Wondraszewski, and today we are looking a little bit more what the term cloud computing means and how it is defined. As part of this class, we will define what cloud computing actually is. We will be revising and revisiting the NIST definition that is being given. We will look at the history of clouds and which technologies enabled clouds. In particular, we will be looking at the service model that promotes infrastructure as a service, platform as a service, and software as a service. When we try to find out what cloud computing means, it's beneficial that you may conduct a cloud search or Google search yourself and look actually up the term, and you will find several different definitions. It's worthwhile to review them to identify what is actually the central part of these definitions and what are the similarities and what are the different. And you will observe then that they distinguish in some sense in the level of details as part of the definition they provide. We are looking here at a number of example definitions, one from Wikipedia, one from NIST, and another one from Gartner. Although we often do not use Wikipedia as a reliable resource for information for scientific information, it is worthwhile to take a look at this and to make sure that the definition of cloud computing, for example, reflects what we believe it is to be. Wikipedia defines cloud computing as follows. Cloud computing is an information technology paradigm that enables ubiquitous access to shared pools of configurable system resources and higher-level services that can be rapidly provisioned with minimal management effort, often over the internet. Cloud computing relies on sharing of resources to achieve coherence and economics of scale, similar to a public utility. This is a fairly interesting definition that has many technical details hidden in it, and we should be reviewing them in more detail. It includes a configurable system, it includes resources, it includes higher level services, it includes the rapid provisioning of these services, it includes that all of this needs to be done through minimal management effort, and all of this relies on sharing of resources similar to a public utility. Public utility, think about the electrical grid as a public utility. One of the things that you also find in that definition is a picture that says contains a lot of applications. There are platforms, and then there's an infrastructure. The infrastructure is the lowest level. The platform is something that you develop with, where you have databases and object stores and libraries, and the application is the actual application that you do. And then another interesting fact of this picture is that naturally we want to interact with the cloud. So we have edge computing services that interact with the cloud, such as your laptop or your server, a desktop, or even your tablet or phone. The most popular definition for cloud computing is summarized by NIST through their special publication. Here we have the following definition. Cloud computing is a model for enabling ubiquitous, convenient, on-demand network access to shared pool of configurable compute resources, in particularly networks, servers, storage, applications, and services that can be rapidly provisioned and released with minimal management effort or service provider interaction. This cloud model is composed of 5 essential characteristics, 3 services models, and 4 deployment models. The NIST characteristics include on-demand computing, a broad network access, resource pooling, the rapid elasticity, and measured services. In addition, the NIST definition includes also a service model in which we have services such as software as a service, which refers to applications that are in the cloud provided as a service. Platform as a service, in which supporting programming languages, tools, services, and libraries are included to provide the platform for development as a service. Infrastructure as a service means that we can provision processing, storage, networks, and other fundamental computing resources on demand. And the next model that we are talking about is the deployment model. Here we need to be thinking about security access and who has access to the cloud. The most restrictive cloud is a private cloud where only a number of authorized users can access the cloud. A community cloud where not only a very small private number of people, but essentially a community has access to the cloud services. Then we have a public cloud in which the general public can utilize the cloud. And then we have hybrid clouds that provide a combination of the three other cloud types. You may have heard about the company Gartner that does business analysis for the business community. And it's worthwhile to take actually a look at the definition that Gartner provides. Gartner defines cloud as the following. Cloud computing is a style of computing in which scalable and elastic IT-enabled capabilities are delivered as a service using Internet technologies. This is a very short and brief definition and has the advantage that it can be easily communicated to other businesses while hiding much of the technological details that are prevalent as part of the service model that is introduced by NIST. However, when we look at this, and we are technologists, and we look at the definition itself, we should probably identify the NIST definition as one of the definitions that we should be going for. But if we need to be communicated and quickly, we can certainly use either the Wikipedia definition or the Gartner definition, as they are hiding many of the details. Let us take another look at the characteristics. Here I'm just listing a couple of general characteristics. Cloud computing supports organizational agility. That means I can quickly adapt to new software or platforms or other activities that are made available by the general community. It is cost reduction favorable because we are sharing resources in large scale, and through sharing we are hoping to reduce the overall operational cost. Cloud computing has also the advantage that it is device and location independent. That means it doesn't matter through which device I actually access this or on which device I run my service. Hopefully that is being hidden through, for example, the platform or the software. And location independence is hopefully doesn't matter where I'm actually running it. This naturally is somewhat simplified because accessing the information in Asia will take longer if the information itself would be lying on a server in the United States. So we need to be still making sure that data services are location dependent. Easier maintenance is being promoted because we are having a reduced number of management staff in order to run our services. In fact, in many organizations, we no longer have dedicated hardware oriented staff because the hardware is being hosted in the cloud. So this, the hope is that reliability is increased, and we can naturally support multi-tenancy on such environments. Thus, it promotes scalability and elasticity because we can really flexible contribute to new services. One of the other important things is because we have to offer these services to the users, the cloud services that are being offered must be monitored, and I must be able to identify how much charge is being done, or in case of a break-in, who has accessed the services. This leads to the security. The hope is that with the expertise of the cloud computing operator and provider, security can be increased. However, this may not be the case because in some cases I actually run into a shared environment, and we need to be extra careful to identify if the security in a shared environment can be preserved. Let us look at some of the characteristics in more detail in a practical application. Let us look how we can actually define the on-demand, scalable, multi-tenant environment for self-serve computing and storage resources. This is being nicely underlined by this graphics that we found. And in this graphics, we are over time issuing how much demand there is. In the server provisioning, the problem can arise that at one point the demand is greater than is being offered by the server, the traditional information technology. Assume we are in a company and all of a sudden we have a high demand on services that need to be conducted in order to serve our community. At one point we have limited resources and we can no longer fulfill them. With the help of the cloud, the hope is that there are so many resources available that this service can actually be provided by the cloud provider. In addition to this is the provisioning of the services itself links to service loads that still can be utilized by others because free resources can be reused by other service needs for other application users. So let us look into how cloud computing came about, and so let's revisit the history of cloud computing. We have to point out that very early on John McCarthy proposed computing such as a public utility, and that was already in 1961. In 1964, when IBM developed the CP/CPMS operating system as well as the VM370, virtualization was being used to share such a particular machine with multiple users at the same time. Mainframes, mini-computers, and personal computers were developed between the periods of 72 to 91, and it was the golden age of the personal computer at that time. In 1991, the World Wide Web appeared, where we are sharing information through networked devices. In 1997, the term cloud computing was coined by Schiloper, but we have to also remind ourselves that similar concepts existed previously, and we need to be looking at earlier developments also. One of the key concepts there, for example, is also grid computing. In the 1990s, where we have 1999, Salesforce and VMware have been created that naturally have a major influence in cloud computing and services and the software offered on it. Amazon Web Services appeared first in 2002. However, we have to remind ourselves that Amazon internally used some of them already much earlier. Google File Systems and Google Paper were occurring in 2003, Google Maps in 2005, then Amazon S3 and EC2 about 2006, Google App Engine in 2008, Windows Azure in 2009, and apps.gov in 2010. Since then, further developments have taken place, which we will be coming into a little bit later. This slide is just a repeat of the previous slide where we had an image about the timeline. Here we just list them in a chronological order. One of the developments that's today often ignored is actually the term grid computing. That is somewhat relevant to cloud computing also. And it's important to understand the differences between grid and cloud computing. While grid computing typically started out with the agglomeration of supercomputing, cloud computing started out on the opposite way, where we are having many thousands and millions of services that are being calculated and served on a single supercomputer or data center. So while in grid computing we have often one user using thousands of resources, in cloud computing we have often thousands of users using very small amounts of computers. When we look at the term grid was actually introduced in 1998 also. We grid computing was introduced prior to 1996 by the Globus project, and a book later on was being defined that summarized the activities in grid computing. And so this whole time an evolution of services took place, and also software as a service was being defined by this community in order to access supercomputers. One of the toolkits that we have, which is essentially a platform for accessing such services, was the Commodity Grid Kit that for the entire time provided an interface to such services as part of a Java implementation. So you could be using this toolkit to interface with these services. And the nice thing about this is if you started doing this early on, you could be unchanged using these services despite the fact that the software was changing underneath, as well as many other services. So the users that developed applications on top of the Java core kit did not have to change anything. So this is a wonderful example for a platform that over a long period of time was being usable by many users accessing grid computing. This is naturally also something that we want to achieve in cloud computing, where we want to have a similar impact. And we will be developing, as part of this class, something we call Cloud Mesh, which is essentially a toolkit for clouds to hide certain aspects from the developer so that they can easily access clouds in a multitude of environments. Let us come back to some of the more recent events in cloud computing and look at some of the cloud computing companies that have recently sprung up in order to profit and to help and leverage cloud infrastructure. In 2006, Amazon entered the infrastructure as a service market, so that you can really get virtual machines on Amazon infrastructure. The Azure platform was created around 2010. Dell, however, already exited the cloud market in 2013 after its initial integration and working on bare metal provisioning tools. IBM made a big push of new software while acquiring a company that is called Bluemix, and our Cloud Mesh software is similar to what Bluemix at that time provided. We also have to recognize that Google entered the cloud provider platform in 2013. And you can now obtain virtual machines in Google, in Azure, Amazon, as well as other providers, and for example also IBM. Other systems that the telecoms initially raised into the cloud computing, but recognized that the market is rather crowded. And we see, for example, exits of public offerings by telecoms such as AT&T, Verizon, and other such offerings. One of the surprising things happened is that HP exited also this market. We assumed through their offerings they would have a very stable platform, and we see, for example, Cisco also exiting. So we have a reduction of cloud companies that offer public services because they recognized that in order to make them reliable and elastic and all the other characteristics that come with the cloud are associated with a significant amount of cost. And it seems to be that only the biggest players in the cloud market can compete in this area. Next, let us analyze some of the influences to the pathway towards clouds and cloud computing. Naturally, we need hardware, and we certainly have also application needs. These are the fundamental drivers to cloud computing. The hardware needs are motivated by the applications. And here we have already pointed out that we have commercial clouds and, for example, scientific clouds and infrastructure. There's a slight difference between the commercial clouds, where we have many tenants, but lots of data, sophisticated business-oriented applications, such as data mining and AI. In the scientific grand challenge problems that we have, and that motivates scientific clouds and HPC services, we see lots of data, but fewer tenants. We see sophisticated scientific applications that have many different but also similar needs as business-oriented applications such as data mining and AI. This motivates naturally that we want to have really big hardware on which we can do this, but we face the problem that we look at the Moore's law, where physical limitations of processor speed exist. We face complicated models of computing, such as provided by distributed computing or high-performance computing. We see that even the agglomeration of multiple high-performance computing platforms as part of, for example, a grid computing environment did not satisfy our need for commercialization because they were just too specialized and targeted just the scientific community. However, they were also very complicated to deploy and implement. We see such a complication also today, as we saw in the previous picture, where many cloud companies actually exited now, just as happened with the grid computing environments, where we identified that in order to run a grid, it takes considerable resources. It takes even more resources to run actually a cloud. We can attest to this as we have used previously OpenStack and other clouds to provide to our communities. And that cannot just be done by a very small infrastructure group. It needs to be done by a larger group. Naturally, influences are being through the virtualization software. Although they appeared early on in the 70s, they have been only fully utilized after the occurrence of companies such as VMware and the introduction of VirtualBox by initially Sun and now continued by Oracle. Other virtualization containers such as QEMU, KVM, and so forth are really important to look at, as well as the introduction of containers and serverless computing. Now, one of the important aspects about how we arrived at cloud computing is naturally the observation of the famous Moore's law. Here we are typically looking at the number of transistors in integrated chip circuits, and we have provided an image here between 1970 to 2016 from a particular resource. And what we observe is that the Moore's law describes the empirical regularity that the number of transistors on integrated circuits doubles approximately every 2 years. And this trend has actually slowed down in recent years. And you can see this on the slide, dip in the curve at the end. So let's take a little bit more precise look at this, what this actually means to our performance, which is certainly important for cloud computing. Let us look what the impact of Moore's law has for an impact on performance. We distinguish floating point performance and integer performance. If we look in the early years before 2004, we find that the floating point performance increased by 64% a year. That is just a wonderful number. We could be guaranteed having faster computers. However, when we look past that, due to the limitations, we only see an increase of 21% per year. The same is actually happening with single-threaded integer performance, and here we look at just one thread because we are living now in the multi-thread environment to outcast what actually happens in the recent years. So we have integer performance of 52% increase till 2004 and then 21% after that. So in order to bypass this limitation, instead of having a single thread on a computer circuit, we have now multi-threads on a computer circuit. Now let's look at some more numbers that are important for our processor performance in general. One of the things that we identified is that Moore's law slows down. We can here plot Moore's law, which we have the transistors in thousands, and we now are reaching an area where we cannot pack infinite amount of transistors into the same area. So we will be seeing a slowdown. One of the other things that we observed, this is based on the spec performance benchmarks in integer, we see a slowdown that now takes place. We saw it also on floating points, as you remember from our last slide. And we see a reduction in frequency. That has also something to do with that we can't make the chips faster, because if they're getting closer together, there may be errors introduced. The typical watt per power is now leveraging off in this time, and the number of cores at the same time has drastically increased. However, we are now reaching an area where also the number of cores is limited, because we are reaching the end of Moore's law. So we need to be very extremely careful what we are doing in our processing pipeline and hardware, and that we find the right balance between the systems. All this leads to naturally a limitation to our hardware that we have available to us. You may now ask, what has this to do with cloud computing, and why would that be important? Well, one of the things that we need to be looking into is not just the pure performance, but trends that actually have arisen recently. You will see that not only Moore's law exists, but that there is a data set growth that we can identify. And as part of this data set growth, we see that it's very linearly increasing in logarithmic scale at this time. Please note that on the y-axis we have a logarithmic scale, not just a linear scale. So the performance in multi-thread reduced, the performance in single-thread reduced, yet the data side is exploding. That means we have to build larger and larger data centers in order to keep up with the data set growth that we are encountering. In fact, there will be so much data at one point that we cannot keep up with the data center size. We need to employ different strategies. Having now said that we have a large amount of data and that we need to be looking into, let's also look at some of the cloud providers and see if you learn something out of that. Well, you have already seen previously that many cloud providers have quit the market and no longer offer public clouds. So here are some of the cloud providers that we need to be analyzing and taking a closer look at one point. As part of the class, we cannot do every single one of them, but you have certainly the ability to contribute to our documentation to pick one of them and analyze what they have actually done in cloud computing. We will be focusing on a small subset of this, such as Amazon, Microsoft, Google platform, and potentially IBM as a platform. Now, all of these companies are activating projects in the area of cloud computing. As we have learned, we are distinguishing infrastructure, software, and platform as a service. And as part of this, when we are looking at the revenue that is being projected within this time, we found one particular study that projects the annual public cloud vendor revenue in billions of dollars. And we can see that particular graph listed here. Not surprisingly, a lot of the revenue is being projected to be in the software as a service, where the highest level of software is being developed. And that is actually the good news, because this is what the cloud is for at one point. We are finding that software is being developed and redistributed, and that's where a lot of the revenue will be coming from. Another revenue stream is actually the platform on which software is being developed. And as you can see, we have an increase in the platform development in billions of dollars. And we also have an increase in infrastructure, because as we said, we have so much data to analyze that it's being put in place, and we need to be developing bigger and greater data centers. Sometimes the differentiation between these components is difficult to assess. We don't know exactly if a large software analysis is also associated with infrastructure, because it's hidden from us. But when we look at this, we need to be addressing this particular problem of developing services in all three areas. And as you can see, billions of dollars are being spent. That means jobs for you. Most recently, we have now identified that cloud computing is being driven by some revolutionary and evolutionary technology trends. Virtual machines is an evolution that took a long time to be put in place. More recently, we see a rapid development in cloud computing, and we find that the software stacks are changing approximately all 6 months. We started out with bare metal provisioning about until 2000, where the cloud was not an issue at that time. And we see that the hardware, the operating system, processes, and software and libraries are all being conducted on one single hardware platform. With the occurrence of virtualization, the hardware could be eliminated from that particular stack, information technology stack, and we only had to worry about how do we virtualize the operating system on the hardware, while processes and softwares are still being conducted on the same software stack that is naturally provisioned on the hardware through cloud infrastructure. Today's we not only have the operating system there, but we have containers. That means we don't actually have the operating system as part of the virtualization software stack anymore, but we are looking now at processes. The newest development that we now see is that we not only have processes, but function as a server as part of serverless computing, in which the function is being developed as one of the activities within cloud computing. That means we have freed ourselves from details such as hardware, operating system, processes, to now functions. And one of the things to notice is you should not just assume, oh, there's only functions, or there's only software as a service there, or there's only process there. It's a combination thereof. An important notice is that although function as a service and serverless computing has increased agility, it has also increased complexity in order to put this into place. This also means that this provides a wonderful opportunity for those advanced students that would like to conduct research and would like to actually get employment in this particular area. Now let's look at one cloud services that's actually offered to us to analyze a little bit about how we got there and what the interest is. Although this is being done by Google Trends, it doesn't mean that this is really a 100% accurate information piece about a trend, but it actually shows some search queries that are being conducted on Google, hopefully being analogous to some trends. So let's see what's actually happening. The first one is the red line, is the grid computing line. This line used to be much higher prior to 2004, but Google does no longer provide data backwards to that data. But we can see that the grid computing has virtually been replaced by cloud computing as a term. And naturally, when cloud computing starts taking place, we see that there's a large interest in it, and we see now it's a little bit less interest in this particular area. And we see also that virtualization has the same trend. So there was a large trend prior to cloud computing being really popular, where virtualization was really super popular. And we see now a slowdown in trend that is similar to in average than cloud computing in general. However, starting 2012, container technologies became more and more popular, and Docker came to rise. A short while thereafter, Kubernetes, a mechanism to run Docker containers on multiple hardware platforms, conjoined via networking, has been created by Google. We see that there is an increase interest in these technologies, and we as cloud computing researchers and also students and activists need to be making sure that we obtain and look at this trend and not stagnate in what has been showcased a decade ago or even just 5 years ago. As you can see, the technology can rapidly change through disruption of new technologies being ingested. As we have already looked at some trends in cloud computing terminology, let's just, for the fun of it, look at what happens actually in computer languages. Maybe there's a correlation to this, either to big data or to cloud computing. What we observe here is that surprisingly, those that want to do only Java programming see that the popularity of Java has today decreased so much that actually Python is much more popular. Even JavaScript that is being used in many cloud-related software applications has reduced on popularity. One surprising notice is that I assumed that Go would become more popular than it actually is. However, Go as a language has some clear advantages that can be utilized to create cloud services. So that's the reason why this class mainly uses Python as the language, because we see the transitioning from Java and JavaScript dominated programming languages to Python. In future, we expect also that a programming language that has been recently introduced called Julia will be much more popular, and we will probably see a rapid uprising there. Julia is similar to Python, but has performance similarities to C and C++.
Now that we have observed some of the trends in Google, let us look at this a little bit more in detail. We saw that in Google we see a peak that slows down. Now, this kind of an observation has been made by a company called Gartner, and it's called Technology Hype, and it's in a much more detail, not just that there's a technology hype existing, but it's essentially hype curve. This is really a branded graph by this particular company, which is a research company, and it represents the maturity, adoption, and social application of specific technologies. The hype cycle provides a graphical conceptual presentation of the maturity of emerging technologies through 5 phases. The 5 phases are displayed here in this particular picture, where we have visibility plotted versus time. We start first with the technology trigger. It occurs a peak of inflated expectations, where everybody wants to jump on the bandwagon and do this thing. Then we learn more about the technology and we go through a phase of disillusionment. And then we really try to engage this technology in our practical work. And we find a slope of enlightenment. And then at the end, we reach a plateau of productivity. So with Java, we saw there was a hype curve, it's going down. And at this time, we have reached actually a plateau of productivity. With other technologies, such as Kubernetes, we are still on the upwards trend because it's the hot new technology. So let's take a look at what Gartner is actually doing. They're doing this to analyze business opportunities and other activities as a research company. Let's take a look at one of these years where they produce such a cycle. Now that we have identified what a hype cycle is, let us take a look at the hype cycle for 2017. Naturally, we don't see here cloud computing on it. That doesn't mean that this cloud computing has become unimportant. It just means it has reached the plateau of productivity and is no longer plotted directly on this curve. However, we need to be taking a look into which technologies on this curve may include cloud computing. So let's go to the list and identify certain keywords that we believe are related to cloud computing. We see artificial general intelligence. That seems like we need to do calculations, so we need to be having cloud computing there. We see deep reinforced learning. It looks like that we need to have lots of calculation and do cloud computing there. We see things such as edge computing. Edge computing provides data and analyzes data on the corner of cloud computing. Smart robots. Well, robots certainly want to be autonomous, but in case they gather multiple data, maybe the data on the computing power that are existing on these robots is too small so that they need to be calculated in the cloud. Think about smart robots that we sent to the Mars. Naturally, they need to be autonomous on the Mars, but the data that is being sent back is being still analyzed on Earth in supercomputing centers. IoT platform. Certainly here, this doesn't mean just cloud computing here, because it's an IoT platform, but the IoT interfaces and provides data that is being analyzed with in a data center. Virtual assistants, certainly there we have cloud computing, because if we have a virtual assistant, it needs to be usable by millions of people. So if you have millions of people, we need to be having the virtual assistant staged and provided somewhere. Connected home, a company that provides certain activities such as light bulbs and so forth that can be controlled in the house is naturally independent. But what about the water meter or other data streams that connects the home to, for example, a utility? Millions and millions of people and data will probably have to be stored into a data center. Deep learning, machine learning, all of those are related to cloud computing in some sense. autonomous vehicles? Yes, because in order for us to make a vehicle autonomous, we also need to be providing it with data that we are collecting, for example, in a cloud. For example, traffic jams are being monitored and being relayed to your GPS system, for example. Cognitive computing, yeah, also there we need to have cloud computing. Certainly blockchain, because we, for example, mine bitcoins. And then let's take a look if you see something else here interesting. Software-defined security, yes, that is being used within clouds. Augmented reality, well, we want to have like an edge device that can actually do this, but for larger things where the current compute power is not sufficient, we probably need a data center. The same is related with virtual reality. So we see that despite the fact that cloud computing is not listed here, it is quite prevalent in the technologies that are being listed on this hype curve. Now let's go through the same exercise that we have done for 2017, but now for 2018. Let's find some of the technologies that seem to be including cloud computing. And we find here potential flying autonomous vehicles. Naturally, they have independent autonomous vehicles in there, but we need to be analyzing data and providing the data to the vehicles, maybe with the calculation of cloud computing prior to, for example, generate maps and other things. Naturally, artificial general intelligence we have here. Knowledge graphs, this is a new trend that seems to be taking place here, and we will be looking into some aspects of this. We have blockchain for data security, certainly. Edge AI, the artificial intelligence units that we have should be employable in edge computing. And certainly these are often autonomous and do calculation on the edge again, but there may be cases where edge computing still has to do AI on actually a cloud service. Conversational AI platform, self-healing systems and technologies. I don't think it has a big impact on clouds at this time. We have AI platform as a service, deep neural networks. We have similar to 2017, all the technologies that we have here still on the hypercurve seem to be listed here, including deep neural networks, IoT platforms, virtual assistants, blockchain, connected home, and some of the reality aspects, so such as mixed reality or augmented reality. So we see there is some changes, but cloud plays still a big role, or will play a role for a long period of time here in our hype cycle. Here we show you the two curves from 2017 and 2018 in parallel. You may want to pause the audio so that you can inspect these graphs a little bit more in detail. Let us now look at the year 2019 and locate technologies that are related to cloud computing. Certainly there are many technologies out there relating to cloud computing. Some of them are not as obvious, but otherwise others such as AR cloud, which is an augmented reality cloud, and AI platform as a service are clearly cloud related. We see, for example, that many vendors are now offering AI platforms on their clouds to attract users into their cloud environment. But we also see other things such as, for example, edge AI, which is related to cloud computing because edge devices are typically connected to potentially clouds. And here we would be executing AI on the edge computing devices in order to relieve cloud computing services from conducting these AIs and to be more responsive while being integrated into a cloud. Other things, such as naturally, if you take a look at this is like a decentralized web, can also be hosted into the cloud, and then there are other examples. Knowledge graphs certainly would be useful to be hosted in clouds, as well as doing the graph analytics, and then dependent on the size of the graphs, you may not have the resources other than in the cloud to analyze them. Let us observe now the evolution of the position of cloud computing in the hype cycle. So here in this picture we compare two observations. First, the position of cloud computing in the hype cycle, and then through Forrester research, the revenue that we have. Let's just take a look at this, and we see here the different years plotted. In 2008 we saw a real strong uprising of the cloud. 2006 things started through offerings of Amazon. In 2010 the peak was reached, and 2017 and 18 we are now in the plateau of productivity. And as said, this doesn't mean cloud computing has now disappeared from the hype cycle. However, if you compare the revenue that has been created by cloud computing, it is absolutely wonderful to see that there's a lot of revenue being created by it. That means not only revenue, but also jobs for you. So that means clouds create big revenue. Technologies that are successful increase their revenue over time. Cloud computing is one of such a trend. And then remember our earlier discussion about software as a service, infrastructure as a service, and platform as a service, where the revenues in these particular areas grow. Rightfully we see a lot of activities in the software developed, but there's a lot of activities in infrastructure and platforms also. And that's where we will be seeing some increased job interests as part of our last slide in this presentation. Another graph Gartner provides is to compare companies with their completeness of vision versus the ability to execute this particular vision. We identify here several areas of relevance where niche players have some ability to execute versus visionaries that have already executed things and have brought to market. The main players we see here is Google, Microsoft, and Amazon Web Services. Niche players are IBM, Oracle, and Alibaba. This field used to be much more crowded. The big window is from July 2019. Versus the smaller picture here from 2017, where many niche players have been disappeared. But we also see that some are no longer being considered visionaries, such as IBM and Oracle. They have become now niche players, and as well as Alibaba. But they have gained on the ability to execute activities. Google has been catapulted from a visionary with somewhat the ability to execute while increasing their ability to execute and following through to their current product line. Now let us take a look at the Gartner trends that recently seem to be important to them, and we are focusing here on this year. And one of the things we already noticed is that the cloud is hidden, and cloud is part of many technology trends, so we really still need to be considering it. One of the exercises I would like you to do as part of this reflection is to identify in the hype cycles in a more clear form which technologies are involved in cloud, pick one of them, and discuss this with us on our Piazza, so that we can include it, for example, in a nice form in our lecture notes. What challenges do you see, for example, for cloud computing, and what should we be researching? So when we look at the Gartner technology trends, we see, for example, do-it-yourself biohacking. Certainly this is bioengineering, and this is, how do you create maybe some brain-computer interfaces, some augmented reality activities, but also biochips and biotech cultures. So for some of them, you will certainly need cloud computing. Identify which one they would be in there. Next, we're seeing an effort of making AI more accessible. That is, we have platforms that integrate artificial intelligence, general intelligence, autonomous vehicles, and so forth. And we observe that many toolkits are being developed, including toolkits on the cloud that provide these AIs as a service to others. And think about this and come up with your own thoughts about how this works, and research this a little bit. A digitalized ecosystem. This includes blockchain, the digital twin, IoT platforms, and knowledge graphs. All of them will involve in some or the other form cloud computing, backup, mining, workflow, calculations. So certainly this is an area where we need cloud computing. Transparency and immersive experiences, 4D printing, connecting a home, edge AI, smart dust, smart workstations, and volumetric displays. These are more consumer related activities. However, if you think about some of them, they need potentially cloud computer to enable or make them better. But it's probably less prevalent in this particular category. Then ubiquitous infrastructure, 5G, carbon nanotubes, deep neural networks, and so forth. Some of them, such as deep neural networks, that are being burned as part of ASICs, certainly do need, in some sense, cloud computing, because we need to be making sure that they are being integrated properly. Once you have these ubiquitous infrastructure, you need to now do and utilize this. It's not sufficient to just increase the speed of the network, but it's also important to create a data center that deals with the increase of the network for example, cell phones. So think about where AI takes place in these emerging technologies, pick one of the topics, and just write a couple of paragraphs about this. That would be really interesting. As we have already brought up Forrester, we need to be looking at some of the trends that Forrester predicts. And here we are focusing mostly on AI and cloud related trends that Forrester observed. And we see first that there's an organization change taking place, and that Forrester sees as important. They say 66% of all enterprises will employ insight centers of excellence as a remedy for organizational misalignments. That means we are trying to streamline the organization, and they are trying to analyze how to make the entire operation better. This includes artificial intelligence and analysis, statistics, and so forth. The Insight as a service market will therefore double as Insight subscription gain traction, because you would like to get insight in your data analysis. Academia will become actually one of the Insight's partners for enterprises, because they provide at this time a large amount of expertise that can be leveraged by such organizations. Naturally, it would be not complete if we are not mentioning artificial intelligence that has recently sprung up as one of the enabling technologies and sciences for this area. We will see that 25% of the enterprises will supplement the point and click analytics with conversational interfaces. Remember, this means that these are fully automated services that are having to be deployed in the cloud in order to make that happen. 20% of the enterprises will deploy AI to make decisions and provide real-time instructions. That's another portion where we need to be thinking about these AI services will actually be hosted in the cloud. AI will erase the boundaries between structured and unstructured and data-based insights. That's our hope, that we will be getting much more insight through AI. So certainly there are lots of AI jobs available, but also in order for us to make the AI possible, we need to have data, and we need to be analyzing the data, and we need to, if we are deploying them in large scale, have AI services for many millions of users that individually analyze their particular case. On the cloud side, we will see that 50% of all enterprises will adopt a cloud-first strategy for big data analytics. That means they are not building a data center locally, but they will go immediately in the cloud to utilize the big data analytics services and or create their own analytics platforms or services. Then when we look at the data, we see that 33% of the enterprises will take the data lakes off life support. That means a lot of companies have gathered data, and what they are doing is they're now seeing if the data that they have collected is meaningful for someone and produce revenue. If they are not produce revenue, they may take off that particular database and let it slide. The majority of the data officers will move from defense to offense. So that means they will be aggressively analyzing the data instead of just looking at it and integrating this into the company to say, oh, we have just a data analysis. They want to use the data rather than just saying, this is all we have, the data. A data engineer will become the hot new job title. 13% of the data-related job postings on Indeed.com are for data engineers, versus less than 1% for data scientists. This is really a startling discovery, because this means that the data scientist alone is not the hot job that you would have expected just a few years ago. Instead, we need to have a data engineer that includes knowledge about the data infrastructure, gathers and collects data, stores data, batch processes them in either real time or in a batch processing, and serves the data to the data scientist via an API. Now, as we can now see, this class is exactly about this. So it is insufficient to just assume someone else will be the data engineer, because the hot new job, according to 2018, will be the data engineer, and within this class, the tools that we learn from cloud computing will assist you into becoming such a data engineer. Let us now take a look at the Gartner Top 10 Strategic Trends for the year 2019. They're separating them in basically 3 categories: intelligence, digital trends, and mesh, which includes also cloud computing. In intelligence, we see everything related to autonomous things, augmented analytics, and AI-driven development. But that does not just mean that everything is being separated. There's lots of interface happening with cloud computing. In other things we have, for example, digital twins, empowering edge computing and immersive experience. And as part of the mesh computing, we see blockchains and smart spaces. We also see trends that go across these identified areas, such as digital ethics and privacy, as well as quantum computing. One of the tasks that we would like you to do is to take each one of these fields and identify how they, or if they are related to cloud computing. To showcase the rich interest in cloud computing, you will find on the internet lots of pictures that integrate a variety of cloud computing companies in particular categorical views, such as for the one that is being provided on the left-hand side, where we have platform as a service, infrastructure as a service, and software as a service companies. These pictures are highly incomplete because if you go further into details, you will find thousands of companies that are actually working in these areas. Some of them are more successful than others. The one on the right shows a particular investment firm, I believe, that looks into what healthcare providers exist, how do you find stuff in education, real estate, legal, energy, manufacturing, non-for-profit, food, government, retail, and transportation and financial technology, and certainly others. So these pictures are very highly incomplete, but you can find more and more information in this direction. Would be interesting to have a comprehensive view of this, but I myself don't have the resources to do that. This may be interesting for a business student as a project to identify what kind of connections even exist between these companies and how they relate to each other. This presentation started with the definition of cloud computing. As part of the definition in the NIST, service models were being introduced. I would like to revisit this service model slightly in order for us to identify more clearly what they're actually about and how they are important, and what the new trend is in these service models, so that we don't miss that new trend. Let us take another look at the cloud service model. I found this nice picture here from the Azure website. And let's remind ourselves that we have an infrastructure as a service, where we have, for example, the data center and physical plants and buildings in there. We have network infrastructure and storage infrastructure and the services themselves as part of the infrastructure as a service. As part of the platform, we, for example, have the operating system, development tools, database management tools, and business analytics that are being, for example, accessed to platforms. And then we have software that uses these platforms to create hosted applications that are being put on the data center in an on-demand provisioning fashion. Let us take another look at the picture. Often the service model is also depicted as a triangular, where infrastructure, platform, and services are appropriately placed. And I put here a couple of definitions that I found on the web, and you may want to reflect upon that. We have infrastructure as a service. It's an online service that provides high-level APIs used for reference various low-level details of the underlying network infrastructure, like physical computing, resources, location, data partitioning, scaling, security, backup, and so forth. Platform as a service provides a platform allowing customers to develop, run, and manage applications without the complexity of building and maintaining the infrastructure typically associated with the developing and launching of an application. So it's a middleware, so I don't have to think about actually infrastructure anymore. I'm just working in that platform. And software as a service is a software distribution model in which a third-party provider hosts an application and makes them available to customers over the internet. So we don't even have to think about a platform or infrastructure. The software as a service is being offered to the user, and the user can use that. However, I would like to alert you of the trend analysis that we did previously. And there we found that, for example, functions and containers play a major role. Therefore, I think it's appropriate to augment the service model with function as a service and container as a service as one of the few additions that we can make. And I've augmented the original picture from Microsoft in the following form and added function as a service and container as a service on the appropriate places. Therefore, we reach something that I call the NIST Plus model, where function as a service and container as a service is being placed in a triangular form here for depiction. And we have for function as a service, which allows the customer to develop, run, and manage application functionalities without the complexity of building and maintaining the infrastructure typically associated with developing and launching an application. The container provides us with the following logic. We have cloud services that allows us to use software as part of the development effort to upload, organize, run, and scale, manage on top of containers rather than virtual machines by using providers' APIs and are called through, for example, web portal interfaces and REST interfaces and other interfaces. I'd like to recall the following graphic from our previous slides, and we will be going into this in a little bit more detail while observing, for example, what another vendor has said about this, and showcase much more detail to this picture. So here we have a different view from a different vendor, IBM, about the cloud computing services model, in which more details are being presented as part of the blocks that we have seen in the previous picture. Here we also compare traditional on-premise, infrastructure as a service, platform as a service, and software as a service. We contrast what is being managed by the client versus what's being managed by the vendor in the cloud. And as we can see here, we see, for example, the operating system as one of the lines between infrastructure as a service, where the operating system is still part of the infrastructure as a service, but everything below is being managed by the vendor in the cloud. The line becomes a little bit more fuzzy when we are looking into platform as a service, because some people include the runtime and the middleware even as part of the platform, while others exclude it and create metadata analysis and libraries that are working on metadata and applications only to be a platform as a service. I believe a platform as a service can be a little bit more than what IBM showcases here. But this also reminds us that it's important that you take with a grain of salt what is actually a definition of cloud. There are different definitions out there. The details are sometimes distinguishing each other between different vendors such as Amazon, Azure, and IBM in this case. Software as a service here has the whole software stack being managed by the vendor in the cloud. And certainly one of the things to consider is the cost. Certainly the hope is that with the increased hosting of software as a service in the cloud itself, the customization costs become lower, and we have an increased value in the overall software stack, while lowering the cost. However, it has an increased standardization. and it could be faster to time. So take a look at these categories. Customization, high in traditional, low in software as a service. Higher costs at the beginning, lower in software as a service. Slower time to value, traditional on-premise, but software as a service is more flexible, more rapid, deployable. Standardization, lower on-premise, higher on software as a service. Lower costs with traditional on-premise when we are talking about software development, and faster time to value when we are going to software as a service through agile integrated development frameworks. So what have you learned today? Let's review. We have heard about different definitions of cloud computing. NIST, Wikipedia, Gartner. The NIST definition is the one that we are going with within this particular class. We have learned about history and future of cloud computing. We have looked at the service model in details and added function as a service and containers as a service. We looked through the trends to motivate them. We identified Gregor's Tall principle to succeed in cloud computing. This class helps you to become a data engineer and not just a data scientist. This is essential for you to find jobs, because currently, as we have identified on some research that has been conducted, the number of jobs available is 13% versus 1%. 13% for the data engineer and 1% for data scientists on a particular job posting site. Thank you.